This video will talk about homogeneous systems of equations and how they are similar and different from general systems you're trying to solve. So a homogeneous system of equations means that our right-hand side is zero. So in terms of just general equation form, write something like x1 plus 2x2 equals 0, x1 minus 2x2 is 0, right? This is a homogeneous system because the right-hand side here is all 0. So in matrix form, this is the form ax equals 0, where I have a 0 vector on the right-hand side. There will be a lot of cases later in this chapter where we'll want to look at the solutions to these sorts of equations. These form the basis for a lot of what we're going to be doing in terms of analyzing very specific systems for certain problems we want to try to solve. Namely things like eigenvalues, eigenvectors. We'll see that later. But what happens to row reduction in this case? Well, in this case, you can do the augmented matrix like you would normally do. And in that case, I would get the matrix A on the left side, because that's how the coefficients fit into the row reduction process and how you make the augmented matrix. But the right-hand side here is just going to be the 0 vector, as it always is, right? For solving ax equals b, your augmented matrix is just A on the left and B on the right. But what do our row operations for row reduction do to this matrix? Well, our operations are, we can swap two rows, we can multiply a row by a constant, and we can add some number of copies of one row to another. And these are our elementary operations from before. But if you look at all of these, none of these will change the right-hand vector here if they are all zeros. If I'm swapping two rows, I'm swapping a 0 with a 0. Changes nothing. Multiplying a row by a constant, well, 0 times any constant is still 0, so that keeps it at 0. Adding some multiple of one row to another means I'm adding 0 plus a number times 0, still 0. So none of these change that vector on the right side of the augmented matrix. No matter what we do, we're always going to have zeros on that side, which means we can kind of ignore them and just focus on A itself. We can take just the matrix A and row reduce it into row echelon form, reduced row echelon form, and just realize at the end we're setting things equal to 0 so we can try to solve the equations afterward. So just row reduce the matrix A and then pair it up with the zeros at the end. And there's only really a few results to what kind of things can happen here. Say we start with a 3 by 3. Basically, the options are we get a row of zeros at the bottom, or we don't. If there are no 0 rows in the row echelon form, then when we reduce A, will look something like 1 number 0 1 number 0 0 1, because there's no other options. If I'm going to end up with no 0 rows, I will look something like this at the end of it. And in that case, since I'm pairing this up to be equal to all zeros, I get x3 is 0, x2 is 0 because that goes to 0, and x1 is 0 because those two both go to 0. Therefore, the only solution to ax equals 0 is x equals 0. That's just it, there's nothing else. Also, we can see from the outset that we're always going to have the 0 vector as a solution, because matrix A times the 0 vector is always 0. That's always going to be a solution. The question really is, are there more? So these equations will never be inconsistent, because there's always going to be at least one solution that is the 0 vector. We can see that fact more clearly when we look at what happens if there are 0 rows. If there's 1 0 row, it's always going to be at the bottom, because that's how you do the reduction process. The 0 rows end up at the bottom. You'll end up with something like that, or something like that. But it could be either one depending on what the equations look like. But in either case, you end up with a 0 row here at the bottom. Now remember, we're setting this equal to all zeros at the end, which means that there's never going to be the chance for this to be inconsistent, because you get inconsistent when you have a row of zeros on the left equaling a non-zero number on the right. If that number is always going to be zero no matter what you do, you can't have inconsistency here. Which also makes sense, based on the mark before, the fact that we always have a solution in the zero vector. But in this case, because I have all zeros equaling zero, that's a redundant equation, in which case there is likely to be other solutions, in fact an infinite number of them, besides the zero vector. So in this case, we get an infinite number of solutions, meaning there are other solutions that are not the zero vector. And this fact of having solutions that are not the zero vector, having non-zero solutions to this equation, is going to be super important later on. So that's the idea behind homogeneous systems of equations. They always equal zero, which means we always have the zero vector as a solution. The main question we're going to want to ask in the future is, are there any other solutions? Are there non-zero vectors that solve this equation? And if there are, it's going to be super important to how we want to analyze and solve certain types of matrix type problems in the future, because those will form a way to describe what this matrix actually does, is when there are non-zero solutions to these homogeneous system equations.